Hello, this is Dr. Baxley. These are the printable lecture notes and the video lecture for Unit 1 in Chem 201P, mostly talking about scientific notation, conversions, and significant figures. You can find the printable lecture notes in Canvas, so I urge you to print those out as you watch the video so you can work some of the problems on your own. I'm assuming that you've worked on some of the materials before in terms of the reading, so I'll jump right in with some of the scientific notation. Remember, the goal in scientific notation is to rewrite a large number or a small number with a single number in front of the decimal place. So we can tackle the first number like this, 3.1459, and then this number needs to be multiplied by a power of 10 such that our decimal number, our new number, will end up being the same as the original number in terms of meters. So this particular number would need to get multiplied by 10 a total of 4 times in order to return to the 31,459. So that exponent of 10 is going to be 4. This works for small numbers too. We again write the number with 2.010. That has to get multiplied by a power of 10 to get the original number. Our new number would have to be divided by 10 3 times, 1, 2, 3, in order to return the original number in liters. So since we're dividing by 10 3 times, that would be 10 to the minus 3. In the next example, this is similar to the first one. This will be written as 2.4900. We'll ignore significant figure rules for now. And that number would have to get multiplied by 10 a total of 4 times. The next number, again, we'd write it as a single number before the decimal point, and then the 2 trailing zeros. And then this number would have to get divided by 10 a number of times, in this case 6, to return to the original value of 0.00006. You can also kind of think of it as moving the decimal place over, 1, 2, 3, 4, 5, 6. And that would be the same as the 10 to the minus 6 that we've got there. One important part of the class is to be able to use your scientific calculator correctly in terms of using scientific notation. So here are a couple of examples. So crack out your scientific calculator and let's get to work. I'd like you to compute this first value, 5.25 times 1.5 times 10 to the minus 7. Entering the times 10 to the minus 7 in your calculator can be a little tricky. Let's look at a couple of calculators. Here are 3 common calculators that you might use for your general chemistry class. Each of these 3 calculators has a special button to use in terms of entering numbers in scientific notation. The TI-30 has an EE button that you need to use as the second function. The other Texas Instruments has an EE button that's not a second function. Sharp and some Casio calculators have EXP buttons. These are the buttons you're going to want to use to get your calculators into scientific notation. For the Sharp calculator, it's a little more straightforward. You would type a number like 6.00, press the EXP button, and then type in your exponent. It could be 6, and then you'd use the change sign button to make it negative. And then it would read in your calculator a number like this. There'd be a blank space, and then -6. On the other 2 calculators, you have to do things a little differently. You would enter in 6.00, you would push the EE button, and then you would have to type in the change sign or negative button, and then the 6. And that would give you a value of 6 times 10 to the -6. Now there are definitely buttons that you want to avoid when using these calculators. Oddly enough, it's the button that looks like it should work, the 10 to the X button on these calculators. I urge you not to use those buttons. Those are for a different function other than scientific notation. Those are for raising a specific number as a power of 10. So use the buttons that are intended to be used for scientific notation, EE or EXP. So let's go back to the question at hand and have you calculate this particular number. Enter it into your calculator. You should get 7.9 times 10 to the minus 7 if you enter this into your calculator correctly. If you haven't entered that into your calculator correctly, I urge you to check. Make sure you use the EE or the EXP button. Check out an online help manual. If anything else you can't figure out your calculator, send me a photo of your calculator. Or better yet, a little video of you entering these kinds of numbers into your calculator, and I'll get it straightened out for you. If you're successful at the first number, go ahead and try the second computation, again using the EE or EXP buttons as needed. This one should work out to be 2.5 times 10 to the 5th. Let's move on and talk about base units and prefix multipliers for the International System of Units. These two tables that you see here are common tables from general chemistry books. They show the base units in terms of quantity and the symbol for those quantities that you should be familiar with for your general chemistry class. We'll use all of these types of units in Chem 201P. The next table shows some common prefix multipliers that will be really important for you to know in general chemistry classes. For our class, you don't need to know the first two prefix multipliers, exa and peta, nor do you need to know the prefix for deci. Deci is really only used very much in England and for people that do blood work in terms of deciliters, but a lot of chemists don't use deci at all. But you should know all the rest of these prefix multipliers, including the symbol for the prefix multiplier, the numerical value for the multiplier, and what that value is in scientific notation for the really big and really small ones. Let's talk about how to use this table a little bit, because sometimes some students get confused. Let's look at milli, for example. One way to use this table is to place a 1 in front of whatever unit you're working with. So we could talk about 1 milli something, and we could use one of the base units like meter. So 1 millimeter, and I'll put a great big equal sign right here in the middle of the table, is equal to 0.001 meters. So as long as you get the equal sign here in the middle, that symbol equals multiplier, the table will sort of sort itself out. Another example would be 1 nanoliter is equal to 1 times 10 to the minus 9 actual liters. Or 1 gigawatt. I know that's not on your set of base units. A watt is a measurement of energy. A gigawatt is equal to 1 times 10 to the 9th regular watts. We can use these tables and these symbols and multipliers to set up equivalencies or ratios. For example, 1 microsecond is equal to, we can see from the table, here's micro, 1 times 10 to the minus 6 regular seconds. One helpful way to remember this is that a microsecond is a really small unit of measurement, and a second in comparison is really big. Well, for small to be equal to big in terms of an equality, the small thing gets multiplied by something large. The number 1 is really large compared to 1 times 10 to the minus 6. So a large times a small is equal to a small times a big. We can use that equality to set up a ratio. 1 microsecond is the same as 1 times 10 to the minus 6 seconds. Or we can write 1 times 10 to the minus 6 seconds over 1 microsecond. So those are some examples for how to use that table. A couple of conversions you should know for this class are that in terms of volume, 1 centimeter cubed is equal to 1 milliliter, and that's also equal to a cc. If you like to watch House or Grey's Anatomy or any of those other doctor shows, you'll often hear someone rush into the ER and say, give this person 2 cc's of some drug stat. Well, the cc is short for cubic centimeter. There's one English to metric conversion that I expect you to know for Chem 201P, and that's 2.54 centimeters is equal to 1 inch. You don't need to know the pounds to kilograms, but it is kind of handy to keep that in mind. I came across this table recently. This table has the same prefixes and exponential factors and meanings, but it gives a specific example in terms of 1 millimeter equaling 0.001 meters. It's a lot like what I did in the table above, but this table has it explicitly right there in front of you. Let's work on some conversions within the metric system. We can look at micro. 1 micro something is equal to 1 times 10 to the minus 6. So a microgram is 1 times 10 to the minus 6 grams. A milliliter is 1 times 10 to the minus 3 liters. A nanometer is 1 times 10 to the minus 9 meters. A centijoule, joule is for energy, is equal to 1 times 10 to the minus 2 joules. 1 megawatt is equal to 1 times 10 to the 6 watts. A centimeter is equal to 1 times 10 to the minus 2 meters. The next one gets a little tricky. This is 1 second, and we're being asked for its equivalent to nanoseconds. Here's nano on the table. We know that a nanometer, or a nano anything, is equal to 1 times 10 to the minus 9 of those things. So let's write that equivalent out. For our seconds example, 1 nanosecond is equivalent to 1 times 10 to the minus 9 seconds. But this question asks about 1 second and how many nanoseconds it's equal to. We could multiply both sides of this equality by 1 times 10 to the 9th in order for the numerical value in front of seconds to reduce to 1 and cancel out. And that would leave 1 second being equal to 1 times 10 to the positive 9 nanoseconds. It's kind of another way to think of these conversions. It's a way that a lot of chemists like to approach them, because in this case, 1 second is equal to a lot of little nanoseconds. A milligram is equal to 1 times 10 to the minus 3 grams. We can get that from the table. A liter being equal to microliters, this is kind of like the nanosecond version, in that we know that 1 microliter is equal to 1 times 10 to the minus 6 liters. So both sides of that equality would have to get multiplied by 10 to the 6th. So 1 liter is equal to 1 times 10 to the positive 6 microliters. And then from the table, we can get meters and kilometers. We know that 1,000 meters is equal to 1 kilometer from the table. So if we wanted to calculate how many kilometers were in 1 meter, we could divide both sides of that equation by 1,000, and so 1 meter would equal 1 times 10 to the minus 3 kilometers. Lots of chemistry books will have other common units and their equivalents. Again, the only one you need to know for this class, and my general chemistry classes when I teach them, is the 1 inch to 2.54 centimeters. But in a lot of chemistry problems, you might have to use other English to metric conversions. It's handy to have one of these tables around for that. You're often not expected to know them, but you're expected to be able to use them. Let's practice a few conversions, just so you have the hang of it. In the first question, we're being asked to convert from milliliters to microliters. The tables that we looked at for the International System prefix multipliers didn't have conversions from one tiny unit to another tiny unit. So what I suggest is that you go from one unit to the base unit, and then from the base unit to the next unit. It would work like this: 0.00355 milliliters times the prefix multiplier. We know that 1 milliliter is equal to 1 times 10 to the minus 3 liters. So now we know what milliliters is in terms of the base unit liters. And then we can easily calculate 1 microliter for every 1 times 10 to the minus 6 liters to convert liters back to microliters. And this would work out to be 3.55 microliters. A lot of students find that much easier to do two conversions you know, rather than try to figure out one conversion you don't know. The next question is inches to nanometers. Our conversion table doesn't have inches to nanometers, but it does have inches to centimeters. And once we know centimeters, we could convert to the base unit of meters, and then meters could be converted to nanometers. This is an example of a pathway that you could write out when you're solving problems to help you get you started before you actually start plugging in numbers. Well, let's go ahead and plug in the numbers. We start with the 1.09 times 10 to the minus 7. We can convert that to centimeters. Once we know centimeters, we can convert that to meters, and then on to nanometer. And if you calculate that all correctly in your calculator, you should end up with 2.77 nanometers. We can check to make sure the units all work out since we've done several conversions. We can see that inches reduce to 1 and cancel out, and centimeters reduce to 1 and cancel out, and meters reduce to 1 and cancel out, and the equation is left with nanometers as the only unit. The next question is a little trickier, and this helps us establish one of my main teaching tips for solving these kinds of conversion problems. I always suggest when you have a conversion problem like this, where there is a slash type ratio, that you immediately convert that to a numerator-denominator ratio, where the numerator is written directly over the denominator. So let's see how that works. Take the 0.00075 milliliters, that's the numerator, and write it directly over 1 second as the denominator. We're being asked to convert milliliters to quarts and seconds to hours. And writing the seconds in the denominator like this can really help some students visualize that the first step might be to multiply this by 3,600 seconds for every 1 hour. Otherwise, it can be problematic to try to figure out where seconds should go, whether it's in the numerator or denominator. But separating out the fraction like this can be really, really helpful. Now that the number of seconds has been converted to hours, milliliters can be converted to quarts. In one of the tables up above, there was a conversion of liters to quarts. And so maybe converting to liters first and then to quarts would be useful. So there's the conversion from milliliters to liters and then liters to quarts. And that answer should work out to be 0.0029, and the units would be quarts per 1 hour. We can check those units pretty easily. The units of seconds reduce to 1 and cancel out, milliliters reduce to 1 and cancel out, and liters reduce to cancel 1 and cancel out. And so the problem is left with quarts per hour as the units. There's one last conversion problem here. An iPhone with a screen size of 4.7 inches and a certain mass, and the question asks to convert that to centimeters per gram. In this particular case, you don't even have the slash fraction. You've got to create the numerator denominator fraction yourself. That would work out to be 4.7 inches divided by 5.04 ounces. And setting the problem up like that, numerator denominator, can help a lot to help you figure out where to go next. Why don't you pause the video and see what you can do? I'll show you the solution in a moment. We can solve this like we've done some other problems. Ounces can be converted to grams, and centimeters can be converted to inches like we've done before. And that should all work out to be 0.084 centimeters for every 1 gram. We can check the units just like before. Inches reduces to 1 and cancels out. Ounces reduce to 1 and cancel out, and the units left over are centimeters and grams, just like we've calculated. Doing significant figures and some calculations is going to be an important skill for you to know. I'm sure you've already done the significant figure worksheets, but here's just an overview of what would happen, and some kind of funny business with sig figs and calculations. Remember, you have to do these in order of operations, or PEDMAS, just like you would do some algebra problems. In the first problem, there's 10 grams minus 2 grams, but with a lot of decimal places. It's often helpful to write these out in a common arithmetic method, like you would do in an earlier grade level. If we set this question up as 10.00 grams minus 2.000 grams, you can see by lining up the decimal place that the answer will be 8.00 grams. But we can't use this 0 because we don't know anything about the thousandths place in the 10.00 gram measurement. So we started with 2 numbers with 4 sig figs, but we ended up with 1 number with 3 sig figs. Once you divide that by 4, you end up with an answer of 2.00 grams per cubic centimeter because we're limited to 3 sig figs with our intermediate answer. The same kind of thing happens with the next question. You start with 3 numbers, all with 3 sig figs, but if you add them up together, you end up having a value of 12.90 grams. Why do we get 4 sig figs out of that? We know the hundredths place of each of those measurements, and we know that adds up to 0 and not some other number. So we actually get an extra significant digit out of that computation. When you have numbers in scientific notation, it's really useful to write them out as decimal form, or at least as numbers with the same exponent. So here's what this problem looks like when the numbers are written out in their decimal form. With the decimal points lined up, we can add those 2 numbers together and get 0.00368, where we know the place for the 8 in terms of millimeters, and so we end up with a number with 3 sig figs, even though one of our numbers started with 2 sig figs. The next example looks like it might reduce to 1 sig fig, but don't forget that the metric conversions like this are exact conversions, meaning that there are exactly 1 times 10 to the 6 micrometers in a meter. It's not 1.01 micrometers or 1.02 times 10 to the 6 micrometers. It's exactly 1 by definition. So this number works out to be 0.01200 meters. So this number works out to be 0.01200 meters, or you could write that in scientific notation. Either one is acceptable. Here's another problem where you might run into some order of operation issues with sig figs. Doing this initial subtraction in parentheses yields a result of 0.10 liters at 2 sig figs. Dividing that by the 2.000 seconds gives you an answer of 0.050 liters for every 1 second. That's the end of the Unit 1 lecture notes. I think we've covered all the typical problems that you'll see in this particular unit. If you have any questions, let me know.